All right, here we go. Unit 4, Lesson 3, solving rational equations. Again, this is just a fancy word for fractions. So we're going to be talking about solving equations where some of the terms are fractions. And the key point is the same as it was last class. Last class, we learned how to add and subtract rational expressions. And the key point there was that we needed to ensure that the denominators were the same. And once you did that, you can just compare the numerators. You can add and subtract their numerators. The same thing is true when we have full-on equations. As long as the terms all have the same denominator, then we can just make an equation out of their numerators. So here's a really simple example. If I said some number plus 2 over 5 equals 7 over 5, well, the only way that's going to be true is if x plus 2 equals 7. See how I just made an equation out of their numerators? X equals 5. Yeah, 7 over 5 equals 7 over 5. What makes this possible is that these two fractions, these two rational expressions, have the same denominator. So we're going to be doing that for a few more complicated examples when we have variables in the denominator. And when we have variables in the denominator, something is going to happen, and we'll get to it when we get to it later, where you're going to have to look for extraneous, right, which means extra, no good, fake solutions that would cause division by 0. So you remember from Algebra 1, you just can't divide by 0. You type it into your calculator, you'd get an error. Because if we try to say 5 divided by 0, and we try to get some answer to that, well, what we're basically saying is 0 times some number equals 5, and that's just not possible. There is no solution to that equation, so you can't divide by 0. So we'll have to look out for that later. But let's just run through some examples in increasing difficulty. So the first would just be the most straightforward case. If the denominators are already the same, then we can just literally kind of scratch them out, right? We can just make an equation out of their numerators. We can just say, okay, well then if their denominators are the same, then x plus 3 has to be equal to 5x minus 9. And you just work a little algebra magic. You subtract the x from both sides. You get 3 is equal to 4x minus 9. You add the 9 to both sides, right? You've done a million of these. We get 12 is equal to 4 times some number x. Divide both sides by 4, you'd get x is equal to 3. And you could check this out. If you plug this in, you'd get 6 over 2 is equal to 6 over 2. And yeah, those are the same thing. The important part here is that I just quickly checked. Does this cause 2x minus 4 to be equal to 0? No, it causes it to be equal to 2. So we're good to go. 3 is a correct solution. And so we're going to have more difficult problems, such as when the denominators must be made equal, right? If you have some division of pizza into 4 sections and I have mine divided into 8, we can't just trade and compare slices. We need to both be out of 8. So you'd cut all your slices in half. The way we do that though, right, is we use this idea that you can multiply by 1 and you don't change what's going on. If you multiply by 1, you still have the same number. But we multiply by 1 in a sneaky form of 2 over 2. Because as long as we're multiplying by 1, it doesn't change what's going on. So what this would give us 2x minus 8. Don't forget to distribute that 2. Everything gets multiplied by 2. 2x minus 8 over 8 equals x plus 4 over 8. Well, now they have the same denominator. Now we both have our pizzas out of the same number of slices. Now we can just say, well then, this is only true if 2x minus 8 is equal to x plus 4. You work a little magic, right? You subtract the x from both sides. You get x minus 8 is equal to 4. You add the 8 to both sides. You get x is equal to 12, right? So we get a final answer here. We get x is equal to 12, a little Christmas theme there, right? And you can plug this in and you can see that this will be true, right? We'll have 16 over 8 on the right-hand side. And on the left-hand side, 12 minus 4 is 8 over 4. Yeah, 8 over 4, that's 2, equals 16 over 8, that's 2. So this does work out. But all I really needed to check was that it doesn't make the denominator 0, which of course it couldn't because they're just numbers. Okay, so just going through a couple more examples here. Don't forget, right, like if you have one term that's rational and one that's not, you can always just pretend this is x plus 1 over 1. And so to make it comparable, we would just have to multiply by 8 over 8 here to make these the same. So this would be equal to 8x plus 8 over 8. And now we could write 5 times x plus 1 is equal to 8x plus 8. And this is getting a little tedious at this point, but you get the idea. 5, because I know how to do this. 5x plus 5 is equal to 8x plus 8. We'd subtract 5x from both sides. So we'd get 5 is equal to 3x plus 8. We'd subtract 8 from both sides. Negative 3 is equal to 3x, and x is equal to negative 1. Once again, I just check. Nope, doesn't make any of my denominators 0. Doesn't cause division by 0. Two more examples. Example number 4. Sorry, that kind of went onto the wrong page there. Multiple expressions, right? So just kind of getting into two of the hairiest examples you might see. We've got 3 different denominators here. One of them's hidden. We've got a denominator of 1 on the right, a denominator of x squared plus 2x minus 3 in the middle, and a denominator of x plus 3. Anytime you see an expression like this, there's almost always going to be a way to make your life easier by factoring. And so if we take a moment and we factor this as x plus 3 times x minus 1, we can see that there's already a little bit of shared denominator here, right? On the left, the only thing that the left one is missing is this x minus 1. So I'll multiply by x minus 1 over x minus 1, then it will have the same denominator. Now this 1 on the right is missing both of these pieces, so I'm going to multiply it by actually this whole thing. I'm going to multiply it by x squared plus 2x minus 3 over x squared plus 2x minus 3. And so I'm going to show you this like fully out once, right? And then you kind of get to see a little bit of a trick here. So the trick is that, or we'll do it out the full way first. So we would need to multiply, right? We would need to distribute this whole thing, x minus 1 times x plus 2. I'll do this over on the side here, x minus 1 times x plus 2. That'll be equal to x squared plus 2x minus 1x minus 2. So that's going to be equal to x squared plus x minus 2. So that's our first fraction, x squared plus x minus 2. And all of this, like we just said, is over x minus 1 times x plus 3. We will be adding that. The only one that we didn't touch was this middle one, but I'll show it factored so we can really see how these are all the same, is equal to x squared plus 2x minus 3 over, we'll show this one in factored form as well. Notice that these are the exact same thing. These are the exact same thing, x plus 3 times x minus 1. Here's the thing. Once you've done enough of these, right, you just start to see it in your head. You're like, wait a minute. Why did I write all of these denominators when I'm just going to make an equation out of the numerators? And that's fine. Once you've done enough of these, you do your multiplications, but you only really carry them out for the numerators so you can see. So we'll do this on, remember these are still two sides of an equation, right? Our numerators all have to be equal. So combining these first two, this will be x squared plus x, and then I'll do negative 2 plus 1. So x squared plus x minus 1 is equal to x squared plus 2x minus 3. And so, a few things are going to happen here. If I subtracted x squared from both sides, well, our x squareds would go away. So I'm just going to have x minus 1 equals 2x minus 3. So I'm going to need to get my x's to one side, my numbers to the other. I'm going to subtract x from both sides. So I'll have negative 1 is equal to x minus 3. And then I'll add 3 to both sides. I'll get x is equal to 2. Woo! And so you could go check this whole equation. It is true. If you take 2 and you plug it in for each of these x values, you would get the same thing on the left and right hand sides of the equation. Now, the only thing you really want to check for is, does this make any of my denominators 0? No, it does not, because we'd have a 5, we'd have a 5, we'd have a 1. It wouldn't make any of the denominators 0, so we are good to go. All right, had to make a cut there, made a mistake in this one. I wanted to show you one last expression that has everything. It's got multiple expressions, and it ends up having an extraneous solution. And so let's start by just going through step by step. If I want to solve this equation, I cannot compare these three fractional terms until they have the same denominator. You might start to just multiply, but you'd run into trouble. And the reason you'd run into trouble is that this is a lot easier if you factor this middle term. This middle term can be factored as x plus 2 times x minus 3. And what you notice when you do this is that each of the other fractions already has a piece of this. So if I multiply the right-hand fraction by x plus 2 over x plus 2, well, then it's going to have a denominator of x plus 3 times x minus 2. If I multiply the left by x plus 3 times x or over x plus 3, then it will have the same denominator. And so here's the trick I was talking about in the last problem. You could write this all out. You could write this thing all out with all of the denominators being x plus 2 times x plus 3. But you know that's going to happen. And then you know the next thing you're going to do is you are just going to make an equation out of the numerators. So you can skip straight to doing that once you've done enough of these and you feel comfortable with it. So all I'm going to write here is that this numerator trio ends up being x plus 3 times x plus 2, right? This one doesn't change because its denominator didn't need to change. And that's equal to 5 times x plus 2. Make sure you have those parentheses there. And so we can just go to solve this out. We'll do our distribution. We'll have x squared plus 3x plus 2 is equal to, don't forget to distribute. That was what happened to me, and now I have to record this again. And so here is a very, very, very important thing in your development of equation solving. When you take a look at this, what you need to realize is that we have x squared terms and x terms. As soon as this happens, alarm bells should be going off in your head. This is an algebra 2 solve. I'm differentiating that. In an algebra 1 solve, you bring x's to one side, numbers to the other, and you just solve down to a single x equals. When there's an algebra 2 solve, that's where you're going to have x squared plus some x plus some value c, and you're going to need to set this equal to 0 so that you can factor and figure out what the zeros of this equation are. And so the trick here is seeing this and realizing what you need to do is to bring everything over to the left-hand side. So the first thing I'm going to do is I'm going to bring the 5x over. I'm going to subtract 5x from both sides, and I'm going to bring the 10 over. I'm going to subtract 10 from both sides. And so what that's going to leave us with is x squared, 3x minus 5x is negative 2x, 2 minus 10 is negative 8. When we do that, we have x squared minus 2x minus 8 is equal to 0. And what this allows us to do is to come up with the factoring, right? Because you could stare at this for a while and maybe come up with the zeros, but it's way easier if you just turn this into x minus 4 times x plus 2. And we see here that these zeros would have to be x equals 4 or x equals negative 2. Now, I chose this example on purpose because I wanted you to see an example of an extraneous solution. Every time you do one of these problems, you need to check each of your denominators and check, do any of these cause division by 0 if I were to plug them back in? And so remember, our denominators were x plus 2, x plus 2 times x plus 3, and x plus 3. And so 4 doesn't cause a problem, right? If you plug in 4, you'd have 6, you'd have you'd have 6 times 7, and you'd have 7. But the problem is negative 2. If you plug a negative 2 into this denominator or into the middle one, you would cause division by 0. And you cannot divide by 0, so this is an extraneous solution. It does not count, because if you go to plug it in, it does not cause a true statement. Again, the problem here is that if you took -2 and you plugged it in, you would get division by 0, which isn't a thing. So the only solution here is x equals 4.